Controlled Environment Plant Production Engineering Technology Education modules are developed and presented by The Ohio State University, Rutgers, the State University of New Jersey, and the University of Arizona, with support from USDA, NEFA through their Higher Education Challenge Grant program. In this module, we'll discuss the topic of data acquisition and control systems. This module is presented by Dr. Peter Ling of The Ohio State University and Dr. Murad Kassira of the University of Arizona. By the end of this module, you will be able to first explain how data acquisition and control system trigger control actions, how a data acquisition and control system works, how an actuator such as a heater can be automatically turned on for heating in response to readings of temperature sensors in a greenhouse. The second objective is to classify sensors. The classification is from power requirement perspective and from whether they are absolute or relative. Some sensor requires external power source to operate, others do not. Some sensors require a reference to make their readings useful, others do not. The third objective of this module is that you will be able to discuss different types of greenhouse controllers. We will discuss different types of greenhouse controllers from the simplest thermostat to the most sophisticated integrated computer control system for greenhouse climate control. There are three basic components in the data acquisition and control systems. From the simplest to the most sophisticated, the components are sensor, controller, and actuator. In this module, we will spend some time on analog systems, but spend significantly more time on digital systems that are commonly used by the greenhouse industry. Again, the three components of a data acquisition and control systems are sensor, controller, and actuator. A sensor responds to some stimulus in the environment by outputting an electrical signal. This signal can be a voltage or a current. Sensors with a voltage signal output are suitable for short-distance data transmission, where sensors are not too far from the controller. On the other hand, sensors with current outputs are better suited for applications where sensors are at a long distance away from a controller. Knowing that voltage drops over long cable lengths due to wire resistance, voltage output transmitted over long distance will have large voltage drop as the transmission distance increases. Additionally, some voltage output of sensors are sensitive to the noise induced by nearby motors, conveyor belts, and radio transmissions. Thus, the voltage signal received by the controller can be significantly different from the voltage signal produced by the sensors. Therefore, current output should be used when sensors and controllers are far apart. In addition to analog outputs, either in the forms of voltage or current, digital output option is available for some sensors. Digital sensors producing discrete output that are most robust compared to the analog outputs. The controller makes control decisions based on the received sensor signal, then send a signal to an actuator resulting in a control action. The decision-making mechanism of a controller can be as simple as a bimetal triggered electrical contact, such as an analog thermostat. More sophisticated controllers acquire data from multiple sensors using complicated data analysis algorithms for making control decisions. We will cover various types of controller later in this module. In the previous slide, we talked about analog and digital sensors. This graph shows difference between an analog signal shown in white line and a digital signal shown in red line. As you can see, the analog signal level is continuous, and the digital signal has discrete levels where the vertical axis value stays the same in between two vertical dashed lines. On the other hand, the analog signal has continuous values in between two vertical dashed lines. For digital greenhouse environmental controllers, analog sensors outputs are first digitized using analog to digital converters before the sensor data is processed for decision making or stored. Next, we'll talk about different types of sensors. Sensors can be classified based on how they generate their output signals. It can be a passive type, or it can be an active type. A passive sensor does not need additional energy source, and its signal output is generated directly by a stimulus. For example, a thermocouple junction generates a voltage, and a photodiode sensor generates a voltage when exposed to light. On the right-hand side of the slide, you will find a type K thermocouple. At the bottom left, a quantum sensor that measures the photosynthetic active radiation level is shown. Sensing principle of thermocouple and photodiodes will be further discussed in other learning modules. Different from the passive sensors discussed earlier, active sensors are powered using external power sources that provide constant voltage or current. Outputs of the sensors are functions of environmental conditions that change resistance in the case of an RTD, or change of capacitance in the case of a capacitance soil moisture sensor. It is important to point out that quality of the external power source may have significant effect on the reliability of the sensor output. The external power source must meet the current and voltage requirements of the sensors. Insufficient electrical current causes voltage drop. An example of this problem is brownout, when light dims due to too many electrical devices running on the same electrical circuit. Voltage variation of a power supply has direct impact on the sensor performance. Providing high-quality external power source is important for active sensors, especially for sensors without built-in voltage regulator. Two examples of active sensors are provided here. Electrical resistance of a RTD is a function of time. The resistance of a RTD increases in response to a lower temperature, and the increased resistance results in a lower current output. Similarly, the electrical output of a capacitance soil moisture sensor is affected by capacitance change that is a function of soil moisture content. Sensors can also be classified by reference. A sensor is either an absolute sensor or a relative sensor. An absolute sensor signal relates to a physical scale where no reference is needed. For example, RTD, or resistance temperature detector, is an absolute sensor. RTD's resistance relates to the absolute temperature. The other sensor type is relative sensor. The signal of this type of sensor relates to a reference. For example, the thermocouple produces a voltage that is a function of a temperature gradient across the thermocouple wires. yet an ice point reference is necessary for actual temperature determination. Knowing types of quantity of sensors are useful for their installation and interface with a greenhouse controller. One will need to know if external power is required and if references are necessary for using sensor outputs. For example, types of some commonly found greenhouse sensors are pyranometer, which is a passive and absolute type. A thermocouple is a passive and a relative type. Thermocouple does not require external power, but it does require a reference to determine its actual temperature. In the case of hygrometer, it is an active and absolute. CO2 sensor is an active and absolute type. Anemometer, in this case a wind cup, is a passive absolute. So for the active type of sensors, external power is required, and for the passive type of sensors, there's no external power requirement. The brain of a data acquisition and control system is its controller. While most modern-day controllers are digital systems, some simple analog controllers remain popular for simple tasks. A mechanical thermostat is an example of a simple analog controller. Digital controllers include either microprocessor-based or computerized systems. We will discuss several different types of controller in the following slides. Let's start our controller discussion with an analog one input, one task type. This is a simple controller. A very familiar example is a mechanical thermostat with a bimetal sensing element. As a bimetal element responds to environmental temperature changes, it closes an electrical contact when a temperature set point is met. In this case, the bimetal strip serves both as a sensor and a controller. The thermostat can be used to turn on a fan, that is the actuator of this data acquisition and control system. Next controller type we will discuss is a digital one input, one task controller. Instead of using analog sensor signal directly by the controller, analog output of a sensor is digitized for the controller before the data is analyzed. Decision made, then send a digital signal output to an actuator. An example of this type of controller is a digital thermostat shown in the following slide. Here are examples of simple controllers. An analog thermostat and a digital thermostat. An analog thermostat has an accuracy of plus minus 2 or 3 degrees Fahrenheit. Its accuracy may decrease with age. Cost-wise, it is inexpensive, is running around $50 to $60 each. Digital thermostat is more sensitive to temperature change with an plus minus 1 degree Fahrenheit temperature sensitivity. Cost-wise, it is around $100 and is more accurate and has greater longevity. This type of controllers are low cost and easy to use, but do not coordinate among each other. For example, single task thermostats do not prevent ventilation and heating from running simultaneously. The simultaneous operation can happen when heating and cooling set points of two independent thermostats are set closely. The next level up of controller type is capable of multi-stage control by triggering either one or more actuators. Multi-stage control of cooling is common for greenhouse climate control. multiple temperature set points are set for controlling different actuators. For example, temperature rises past set point and a vent is opened. At the second stage, the temperature continues to rise and the fans turn on. In the third stage, the temperature continues to rise and the cooling pad will turn on. This type of controller can also have independent night and daytime temperature set points. It can also trigger alarms in the case of a problem. As we are moving up on the technology ladder of the controllers, the next level up is a multi-stage, multitask controller that may have data recording capability. This type of controllers monitor multiple environmental conditions, control multiple actuators, and can be used for implementing crop-specific growing strategies. It can be used to control irrigation, cooling, heating, and lighting for meeting the specific needs of different crops. For irrigation, the system controls when to turn on and for how long. For cooling, vent opening angles can be a function of temperature gradient between outdoor and indoor air temperatures. Further, this type of systems has ability of using weather station information such as outdoor temperature for the vent opening angle control, and outdoor wind speed information from the weather station can also be used to protect greenhouse structure by closing vents under high wind conditions. Data recording ability is another valuable feature of this type of system. The top step of the greenhouse controller technology ladders is this multi-input, multitask integrated controller. This type of controller is computer-based that typically offer easy-to-use user interface so that users can change control strategies easily with key entries. Operations of the actuators can be controlled using on-off, proportional, PID, or other control algorithms for system performance optimization. Coordination of control action is also possible. For example, there are many options for cooling a greenhouse if it is well equipped. Cooling options include shade curtain, evaporative cooling devices, exhaust fans, and vents. An integrated computer controller can be used to select the best cooling method for the given situation. More discussion on the greenhouse climate control strategies can be found in another learning module. This type of controller can also perform anticipatory controls that are using mathematical models to predict crop growth, greenhouse climate conditions, and resource requirements. For example, precision irrigation management of when to water and how much water can be determined using water demand estimated from evapotranspiration models. Simple as well as sophisticated evapotranspiration models are available for the weather-related water demand estimation. An integrated controller can control multiple zones, multiple tasks at different set points. Typically, it runs on a personal computer and is accessible remotely. It can analyze collected data and make decisions. It can anticipate the greenhouse climate based on outside data from a weather station. An integrated computer controller can be used to consider multiple consequences for control actions and for conflict resolution. For example, there are interactions between light and temperature. There are interactions between watering and pest management. In our greenhouse operation, there are occasionally climatic parameters to demand counter actions from control processes. An example of this is for humidity control, when ventilation is on to reduce humidity, while for temperature control purpose, the ventilation is shut. In this case, an integrated computer control system will have to make decision to resolve the conflict between the two demands. This slide shows a schematic of how a digital data acquisition and control system works. As we have discussed earlier, there are three basic functional blocks: sensors, controller, and actuators. In the sensor block, we have discussed various types of sensors. In addition, I would like to add that sensor signals may need amplification for long-distance data transmission. On the controller block, I added more details of handling multiple inputs and hardware requirements of analog to digital and digital to analog converters. Also shown are relays needed for turning on actuators such as motors and heaters using low current signals for a controller. Thank you for viewing this module and hope to see you again soon.